So, welcome. It's another rootkits presentation. 2 years ago it was about rootkits. Again, it's about rootkits. This time I'm not sick, so it's a good thing because I can present the insane number of slides that I have for you today. Who am I? If you don't know me, I'm playing with Macs since 2007 when I bought my first Mac. I do a lot of reverse engineering. Then I started a blog, which was mostly dedicated to breaking copy protections. Usually when I download a new program, the first thing I do is breaking the copy protection just for fun, and then I test the program. I'm not a Mac zealot. People get a lot surprised when they ask me, which phone do you have? And I tell them, Windows Phone. What? You are the OS X reverse? Yes. So I use whatever works, whatever I like, so I'm not a Mac zealot. If you want to learn about rootkits, I wrote a very long rootkits articles for Macs, for Frag, last year or something, was released. It's very long. You can learn a lot of stuff. I'm writing a book, or I'm still trying to write a book, me and two other guys. It takes a lot of time. Hopefully it will be out this year or early next year. I think it will be worth the wait if you like this stuff. I have the really bad habit of creating too many slides. This one has 172. It's not my highest one. I think last year I did 180 or 190. Usually the guys with the time are like, yeah, 10 minutes. If you go see the C-Scan presentation, you see Thomas Lim telling me 5 minutes, 10 minutes. 2 years ago, they did the whiskey con, and I took like 6 shots of whiskey. You can also see that because I kept talking and I totally, I couldn't stop and I wanted to do it, so keep drinking. And the fun part in Portugal, I'm trolling the world with my domain. Only Portuguese, Spanish, and Brazilian understand this one. It's very funny because now you have these guys linking to my domain. You have CNN, you have registered a lot of stuff, and my really fun stuff is going there and see the link to my domain with the footage. The register also makes nice headlines. I just noticed this one: Apple hacker reveals cracker 0-day rootkit whacker. These guys are so what's up? I'm going to talk about how to load kernel rootkits, essentially bypassing all the protections that Apple has. I presented this the first time last year in Japan and in March in C-Scan. I'm doing another presentation based on the EFI stuff that you probably saw on all the news because everyone was very happy and probably Portuguese research breaking stuff. I released the 0-day. If you want to have a very interesting 2 blog posts, if you want to learn about EFI, go to my blog and you can learn. And then you can, in a week or 2, you can see the slides about that presentation. You can talk or you can discuss if these are backdoors or not. They are mostly design and implementation flaws because Apple usually doesn't know what they are doing. They continue to be unpatched kernel vulnerabilities. I'm going to show you that the patch for UseMyT that was released this week still have these 2 vulnerabilities. So Apple does my job, makes my life very easy. Because I don't need to update the slides, they still work, the code still works, it's amazing. And even more funny, which is the second one that I'm going to, or the third one, they put some features that we can abuse to bypass all their protections. So it's, I don't know if you can call it backdoors or not, it's your choice or decision after you see this presentation. Assumptions. If you know me, you know that I'm an economist. Economists like to put the assumptions. You know they fail because you have the IMF failing with their assumptions. So, but we still like to do this. This is our model, so this is where we work. So this presentation assumes that you already have boot in the machine. So I'm not trying to exploit macOS. I can show you, or I'm not going to show you because it's another 0-day stuff. But it's not that difficult to get root in macOS. If you try to estimate the probability of this happening, I can discuss with you like very fast because I have the 0 days for that, and I can show you the proof. But anything below high is probably wrong. You cannot say it's medium or it's at best like Windows. Everyone says bad mouth about Windows, but Windows, the chances are probably much harder than in macOS. For example, I didn't update these slides, this part. because once again, Apple does my job, my life easy, because this week they released the patch for 10.10.4, and if you go see the amount of vulnerabilities that they patched, it's insane. A few more from this guy, from Ian Beer. So you have a single guy from Google, Project Zero, Ian Beer. Like in 2 or 3 months, he got like 10, 20 vulnerabilities, 0 days with root, with kernel, code execution, all kinds of stuff. One guy. So you can imagine how things are. Then you have funny stuff. These are finally patched, but you have funny things like this. They patch the vulnerabilities in iOS, but they don't care about OS X. And they put this, like, they release a bulletin saying, patch it in iOS, in macOS, they don't say anything. When I did this presentation, for example, this vulnerability for which Project Zero released an exploit, a fully working exploit that works without any problems, flawless, they had already released the fix for Yosemite because they got the bug from Google. But from Mavericks, they didn't release any patch. So you had a fully working exploit out there, reliable, working, and Apple doesn't care about that patch. We have also this, for example, another example from a Korean guy, a friend, Trimo. He's very good. And he has a Safari browser remote code execution with full local privilege escalation exploit. So you go to a page, your Mac is over, he has root on your machine. It still works. Much easier ways to get roots. See, you cannot discuss this with me because I will win this fight with you. You can just ask the user, the stupid Mac users, give me your admin password. And you got this malware, iWarm, that infected more than 17K people just by asking them, please insert your admin password, that's it. Game over. More fun stuff. You have a lot of installers and updates going over HTTP. So if you are a guy that the NSA wants, you probably shouldn't download this stuff over HTTP. You have applications installed with wrong permissions. For example, they install themselves with the SUID binary on the machine with that permission, so you can overwrite, you can play some games, and you can easily privilege escalate. For example, there's a backup app for Mac's Carbon copy cloner that you can exploit. The first time the user executes and gives the permission, you can do whatever you want. So the question is, the attack surface is really big on Macs. So the assumption that I do that getting root is not that difficult on Macs, so we can continue on the rootkits. So my goal, since I like rootkits, especially the kernel rootkits, because it's low level and it's way more fun than userland stuff, is I want to load that code. Is it a problem? Well, Apple introduced a new policy. Basically, they introduced code signing in Mavericks. In Mavericks, it's not mandatory, meaning if you try to load some kernel code that is not signed, it will complain, it will say this code is not signed, but I will load it anyway. It makes some sense because it's the first time they introduced this, so they want to test to see the effects of this. Finally, in Yosemite, this is mandatory. If you try to load a kernel code that is not signed, it will not load. So these are 3 reasons why that code will not load in the kernel. First, there's no code signature, so you cannot load anymore if you don't have a code signature. If that code signature is invalid, you can't load because it's invalid. There was a trick that you could really load your kernel extension very early in the system. Apple doesn't have that feature, so if you are, for example, building a security product, this brings you some problems. So basically, you would put your bundle name as com.apple. Now they do certificate verification, so you cannot use this trick anymore. What are the solutions? The first one is what the spies are using. If you are up to date, for example, NSA or the guys that do Stuxnet and Nuku and all that stuff, they are basically really sealing the certificates. For Apple, it costs you $99 to get a certificate. Then you need to make a request and tell them, okay, I want to build a kernel driver. The trick is, tell them it's not for testing. If you say it's for testing, they will deny the request. You just say, I want to build a security product, and they will give you the right certificate. You could disable that feature. I'm not sure if in Yosemite it's still available, or in El Capitan if it's going to still available. If you want, you can disable as a boot parameter. You say disable everything. You can attack from the E5. This is where I'm moving now. This is a really fun world, and essentially, if you can run code at the firmware level, it's game over. You can do whatever you want. Oops, stupid firewalls. You can attack userland demons. This is really stupid. You are going to see how good Apple is doing stuff. So you can exploit kernel vulnerabilities, because if you can find a way to write to the kernel memory, you can do whatever you want. And you can abuse the existing features, which is what I'm going to show you last. Userland demons. These are Apple guys doing security features. They have no idea what they are doing. Case in point. There's a daemon in macOS called KXD. What it does, it's the daemon responsible for doing the code signature check. So when you want to load the driver, it sends a request to this daemon goes to verify the code signature, says yes or no, and that's it. The funny detail is that this daemon is running in ring 3. Basically, it's running at the user level. So it's not running in the kernel. So what you have is something verifying code that you want to load at a lower privilege from a higher privilege. This doesn't make any sense, because you can attack that process. If you attack that process, it's game over. They don't seem to learn. There's a rumor, or there's a guy saying, we are going to, or there is a request for moving this to the kernels. So they are building a new feature in El Capitan. You probably heard about it, rootless. If they leave this like this, it's still there in the beta versions, it's still like this. If they leave this, it's game over. You just patch this and that's it. What you need to do, this is the piece of code that you need to patch. There's the call to that function, static code check validity. This is the certificate related stuff. Essentially, it asks the code to check the certificate, see if it's valid, return yes or no. So what you do, you attach, for example, to the process, patch this code, put a short EX or whatever you want to do, what is your way of patching stuff, and that's it. You can load everything to the kernel that you want, code with code signature or not, that's it. So you really just need a few bytes and you bypass this stuff. I wrote about this, it wasn't this specific attack in 2013, it was a variant for Mavericks, because Mavericks would load anyway. At that time I just patched the warning, because it would show a warning to the user, this kernel extension is not valid, so just patch the message never appears, and that's it. So it's more or less the same variant about this. So I was showing this to Apple guys in Infinite Loop, and they were laughing. They are really nice guys, I don't have anything against them, but they really are potheads, it's hopeless. So my presentation could essentially end here, because patch this, game over, that's it, there's nothing else to do. But I like to explore stuff, and I like to teach people, or try to teach people, and find new stuff. I love this slide, because it says a lot about the security field. You have, in this corner we have firewalls, encryption, antivirus software, and in this corner we have Dave. The Dave is the human error. So basically the human makes errors, and it's part of the game. This is always happens, and so as long as there are humans creating code, there will always be vulnerabilities. So we are going to exploit them. What I'm interested in anything, and in any kernel vulnerability that allows me to write the kernel memory. For example, you can get some buffer overflow or some primitive that allows you to write anywhere in the kernel. You can get some interesting stuff that is from the specific to the Mac, which is the kernel task port. This comes from the Mac design, and there is also the host privilege port. If you have access to these ports, if you have this port, you can do whatever you want to the kernel. In the design of macOS, in the Mac kernel, which is part of it, every process is represented by a task. A task is just a container of data. Then there's a one-to-one correspondence between the task and the process, because the process is a BSD process, but the task is the general container. The kernel is also a task. And you can think about that as PID 0. This concept doesn't exist in other machines, if I'm not mistaken. In macOS it exists, it's the PID 0. So, more fun stuff. Before Snow Leopard there was a bug, or there was a feature. Essentially, you could access the kernel using the task4PID. The task4PID retrieves the task port, you give it. I want this PID, give me the task port, and you can access to that process. So you just say, give me the task port for the kernel, and you'll get that, and that's it. You have this described in that FRAC article. There was no science, because you can write to the kernel. This is the function. And two guys, I know them. They're TT organizes a conference in Taiwan, and they report this very interesting vulnerability. The processor set tasks. And insight is also easy. And when I saw this vulnerability, it rang a bell inside my brain, and I didn't know why. And someday I was browsing this book. It's one of my books that always sit on my desk. It's very interesting if you are interested in the internals of macOS. And I was browsing and I saw it. The vulnerability was there since the book release. Nobody noticed it, but it was there. So insight is always easy to, after you know things, everything is very clear. What the vulnerability does is gives you access to the kernel task port, which is the same result as the task4PID. This is the function, processor set tasks, it calls another function. This one, it has a lot of code, and essentially what it does, it goes over all the tasks that are running into the system and returns that port into an array. There's the funny stuff that we have there, which is the defined secure kernel. I will show you what this means. This is how you get the task ports. You need to get some ports. This is one of the reasons why you need the root access, because to get the host port, you need root access. So if you have root, we can do this. And you get the kernel task port just from the first element of the array that is returned. It's that port, so it's very easy to get. As I told you, this is still not patched. I was expecting this to be patched at least in El Capitan. It's still not patched there. The latest patch for Yosemite, it's also not there. I have no idea why Apple is not patching this. They know because I was showing the slides to them in right there in one infinite loop. This is a bug, fix it. And I presented two times. And they say Yosemite is every bit as powerful as it looks. I say it's every bit as vulnerable. So it gets funnier because they know about this bug. Because that's what the secure kernel define is there. Because this bug doesn't happen in iOS. So they are patching the bug in iOS because they understand how powerful the bug is in iOS. Because if you have this port, you could write to iOS and jailbreak would be much easier. I tried to patch this bug, and there are no side effects. Your Mac will work without any problem. So I don't understand why they are not patching this. So let's get to the fun part, how to exploit this. What we can do if you get the kernel port, what can we do with this port? We can allocate kernel memory, we can read, and we can write and modify writable memory. I will show you what I mean by writable just in a bit. We cannot change the memory protection of kernel code and some data sections because they are made read-only. And we cannot execute code because we just have access to the task port, but we are from a different task, so we cannot change the pointer or directly the kernel pointer to point somewhere else, so we need some tricks. What are some kernel protections? The Apple guys are really bad at security, but they implement some stuff, or slowly, but they do it. The kernel code is read-only. Okay. You know, Apple snitches connections to back home like crazy. The kernel code is made read-only, but this is at page level. So you can see this is the code from the kernel that when the kernel is initializing, it changes the page table to read-only. This is the reason why we cannot make the code, we cannot change the permission, because the function is from a higher from a higher level, and if you try to change, it cannot, because the protection is at page level. The same happens to data sections. They were made read-only. For example, before you could, since the data section is writable, and you have, for example, the syscall tables and the marktrap tables there, you just need to modify a pointer and you can get code execution. Now they are read-only, so you cannot attack the syscall directly. This also happens in Linux. Linux had the same vulnerability. You could attack the table because it's writable. Now it's read-only. There was also another trick. They made the table itself read-only, but there was a pointer to that table that was writable. So what you do, you create a new table, you put everything there original, you modify the pointer that you want, and then you change the pointer that points to the table. That's it. The technique is old. It's called the shadow syscall table. It comes from Linux. I think it was some, cannot remember the name, but it was a Linux rootkit that implemented first this technique. They fixed this. They moved most of those pointers from that section is the God section, so you cannot attack anymore like this. You cannot do a shadow table in Yosemite. You can do the same in every version before you can do it. This is the data section being made read-only. Also you have the non-execute, the data protection. You cannot execute code from there. It's the protection is made at page level. This is basically best practices. Probably all this stuff was introduced by PAX and GR Security, because they are the guys that did most of the innovation last years in security. If you know this low-level stuff, it's possible to override this protection, because there is a register, CR0, which is the control register, which if you change that bit, the WP bit, which is write protection, if you set that bit, the kernel will not kernel panic if you try to write to a read-only page. But this brings a chicken and egg problem, because to change this, we need to execute code. But we cannot directly execute code yet. Then you have also the kernel ASLR. This is not very difficult to bypass. In OS X, you have a syscall, the KAS_info, that will give you the offset of the ASLR. In iOS, this is made. This function doesn't exist. Once again, I don't know why they implement this in OS X. You can have infolinks, which is what everyone is paying based on to get the slides, infolinks. And you have something else. There are other techniques. I already wrote this chapter for the book. I did develop a new technique. When the book is out, you can read about it. So it's not very difficult. It's easy. Easy things usually work most of the time. So my goal is to execute kernel code. I already told you about the amount of problems. We can't execute code. We can't use the syscall tables. We cannot do that trick. In the Mavericks or older, we can use the shadow sys table, which it's very easy to implement. So for those, it's not a big problem. I want you to show you a live demo. That's why I need internet. The kernel extensions, you could try to attack the kernel extensions, because you have the kernel and the kernel extensions. They are also protected. They are made read-only, so it's not interesting to attack. What is the solution? Beacon. If you come from the rootkits, you know that this means direct kernel object manipulation, which is finding data objects in the kernel that you can change, modify, that do something that you want. The goal here is to find a writable data structure that we can modify, and that somehow leads us to code execution. We can execute a small shell code and disable the CR0 protection, and then we can do whatever we want in an easy way. Or you can execute more complex code, which means a full rootkit from there. I don't have much time to speak about this, the trusted BSD. I will just give you a very quick introduction. It is a mandatory access control framework. The project started in FreeBSD. Apple ported parts of it to macOS. The project is called Trusted BSD. MACF is a subset. I usually call it trusted BSD just for briefness, but the framework that Apple ported is the Mac framework, the part. It is the basis for OS X and iOS sandbox. For example, the gatekeeper and the code signing also use this. The latest feature, rootless, in El Capitan uses the same. Rootless is essentially a global sandbox. It has an engine, a decision engine that says, I want to write to the system folder, which is protected. It goes to the kernel, asks on the list, is this authorized to write to this place? Yes, no, and sends back the response. If you are used to exploiting, you already know that how to exploit this, because there will be, for example, update processes need authorization to update the files. So attack the update process and you attack rootless and you bypass all that stuff. It has many hooks available. I really love this framework. Apple is closing access to it. They say it was never made public, and now they are doing some internal changes and they are closing access. This is a very powerful framework because you have many hooks in the kernel that allow you to control a lot of functions in the system. So you can build, for example, your own module to control stuff. If you go to my GitHub, for example, there's a module that if you try to execute a SUID binary, it will send you a warning back saying, this application wants to execute a SUID binary. Do you want to allow? Do you want to deny? Do you want to whitelist? For example, PS process you want to whitelist. It's a warning, it's some more information. I also did something to annoy the hacking team guys. It was the presentation at WhiskeyCon. I don't like hacking team if you follow those guys. And it was based also on this framework. So it's very powerful. You should take a look. I have a really annoying, I'm a really annoying Apple. Don't post this stuff because I love this stuff. So we can add policies. You just need a kernel extension that has a policy model. It has writable data structures, and it leads to code execution because it's essentially a callback system. You put your callback, and your code is executed under certain conditions. How can we use this to exploit? We have a new policy with a single hook. We just need one code execution that will point to our code. This could be the shell code that disables the CR0, or it can be the full rootkit in memory. And then we call the function that we have the hook, and that starts the rootkits. Let me quickly go on what to do for this. The steps. We need a kernel test port because we are writing to the kernel. We need to find the slide because we will need to change some stuff, and the kernel and the data structures are somewhere. So we need this. We need to compute the rootkit size because we are going to copy and install it in memory. We need to allocate memory to put the rootkit there, or we can find some free space for that. Then we need to copy the rootkit to kernel memory. Remember, we are executing from user land, and we have to put somehow the code in the kernel. Then we need to change memory protections, because if we allocate, the memory is not executable by default. Then we need to fix the symbols, or external symbols. This is the funniest part, or the more interesting part, at least this one, because we are bypassing the kernel linker, so we need to basically implement our own linker. Then we install a new trusted B policy and execute the hook to start. And you probably want to clean up so the forensics guys don't know what's happening there. I like a lot the forensics guys. I'm not sure if you use volatility. For a while I was playing with volatility guys because they have an assumption. They think that they can find everything because it's on memory. And I showed them a few times or a few vulnerabilities on that stuff, and they will not find the kernel rootkits with their software. So don't trust your tools. I did talk about that. Don't trust your tools. Always be suspicious about that, especially if you are trying to chase rootkits. Remember, I'm running on a level probably lower than your tools, so I can manipulate all your tools. So don't trust them. Use them, but be very suspicious about those tools. This is the code that I already showed you to get the kernel test port, nothing difficult. This is the code to get the slide using that function, the KS-info. This is basically inline assembly. You can import the function. It's not very difficult, nothing very complicated. To compute the root key size, there is a small trick. Usually, the size on disk is different from the size on memory because alignment reasons. So if you want to compute the root keys, because we are putting on memory, we need the memory version. So it's basically use the field that gives you the size on memory and not on disk. Because if they are different, you are going to get problems. To allocate kernel memory, there is a function, the MAC. You will see a lot of functions, MAC. On the kernel, these are functions that use usually the task port that deal with the MAC layer or are MAC traps. Essentially, what we need memory somewhere in the kernel. We don't care because we are controlling a full pointer. We are not playing with offsets, so we have 64 bits absolute address. So we just need memory somewhere. You use the function, the kernel port. You see that the first parameter is the task ports. You can use this function, for example, to inject code into any program. As long as you have the port of that process, you can do whatever you want. And then we put size and everything else. There are some problems with this because if you use this function like this, for example, if you try to allocate 100K of memory, this will crash your system. What happens is that the whole memory is not wired. Wired means that non-wired memory, it can be paged out to the disk, even from the kernel, it happens. And wired memory is always there physically. For example, the kernel runs in wired memory, because if you had a page out or a page in on the kernel, you could risk running the pager to the paging system, to disk, and then there's no code to do that. So this is the reason why there is kernel panic, because the kernel will not copy everything when you copy. It says, it lies to you, it says, I copied everything, but everything is not there. If you try to execute code, you'll sometimes land into kernel panics. If you are trying to execute just a small shell code, this is not, for example, a page is good enough. For some stuff, 4K is too much. Bill Gates said that 64K it was too much, but 4K sometimes it's more than enough shell code. So the result is page faults. What is the solution? The solution is very easy. You just need to make that memory wired. There's a kernel function. You tell it, this piece of memory that I allocated is wired. Do not page out ever. It has a small trick. First, you need to set the memory protection. So first you say, this memory is going to be executable, readable, and writable, if you need. And then you change the wire status with this function. If you try to do otherwise, you will get this function giving an error and you don't know why. I spent some time this and then I finally understood what was the trick. To copy the rootkit, another MAC function writes. You tell it, I want to write this data to this process at this address. We already have the address. We know where the rootkit is because we allocated the memory. So it's basically a memcopy in the kernel using the MAC function. Same for changing memory protections. You have a function called MAC vmProtect. You probably want to fix, for example, data areas to not be executable. This is, once again, to avoid forensics, because if you start seeing, if you are changing something and you see, for example, lots of memory that is read, writable, and executable, this is very suspicious. So you want to put things as normal as possible. Once again, use the virtual memory size field because alignment reasons, and this is what you will allocate to. To fix the external signals. Because there is kernel ASLR, the kernel code must be PI, position independent. So you don't need to change the offsets. Everything in the kernel, in the kernel extension code and kernel is based on offsets. So a function is called with an offset, so you can put the kernel anywhere you want. The offsets stay always the same. So there is no problem with this. What we need to worry about is the external symbols. This is the equivalent in userland for a library. Usually you link in C if you are doing for Linux or any Unix system, for example, stdlib to get functions, system functions. You do the same in the kernel. There are, for example, string functions that you can access and memory allocation functions and so on. Because we are bypassing the kernel linker, we don't use the kernel linker, we are talking directly to the kernel. We need to build our own kernel linker. This is very complicated, maybe. I was like, yes, this is going to take me a lot of work, and I don't want to write a linker myself, but in the end, it's very easy. You have all the information, you have the relocation tables. These are the same tables that the kernel linker uses. It needs to know what needs to be fixed. You have the same information in all other formats. P has the same information, ELF has the same information. You can find this information in those two commands. The dynamic syntab and syntab, it's there, the location where this table is, all the symbols that need to be fixed, and so on. Complexity. There are 10 different types of relocations, and you can start thinking, okay, this is going really to give me a lot of work. But in reality, there are only two that you need to fix. One is relative addressing. This is, if you are used to reversing stuff, this is basically a 32 bits offset to somewhere using the current instruction pointer. So the offset is basically the instruction pointer address plus the instruction size, and offset minus or plus the offset. And we also have some relocations which are absolute addresses. These are easy because you just need to say point to this address and that's it. I know this because I built a small utility to go through all kernel extensions and get the number of symbols. And I know only those two types are used. There are two types: external, which are the symbols that the linker does, and local. Local are strings, for example, that you have on your code, if you have, and some other local kernel extension symbols, for example, the start and stop functions, they are there. So this is not very complicated to do. This is some code that locates the tables, then finds the symbols to which they correspond to, then tries to solve the kernel symbol to locate the target symbol. For example, I want to do a memcopy. I need to find where that memcopy is in the relocation table. I need to find where the memcopy function is implemented in the kernel, and then you just need to fix the offset yourself. This is what the linker does. When it's linking, it's basically doing this work. This is a piece of code that does that. I left this on purpose. It has a bug because the offset here is 32 bits in an integer, and there is no guarantee that this offset will be enough. It can overflow, and it will point to somewhere else. The reason for this is that we are locating the kernel somewhere else in the kernel, so we have no in kernel memory, so we have no guarantee that the address where it is, it's 32 bits away from the kernel, and this is an integer, signed integer, so we have half of the space half of the offset. I left this here just as a warning. What we can do is using a trampoline. For example, you can jump from the kernel extension to some space. You allocate, when you build the kernel extension, you allocate a space for an island that is executable. You jump there, and from there you can use an absolute address because you have enough space and jump anywhere you want. So we are basically redirecting the flow of the program. So it's not very difficult to implement. It's a very easy way to work around the problem. These are the absolute addresses. These are very easy. You find the symbol where the symbol is, and you put the whole offset, the whole address, and that's it. These are very easy to process. These are related to the local. It's essentially the local ones are always absolute addresses, so they are even easier to fix. So to build your own linker, it takes like 200 lines of C. So as you see, it's very simple. it appeared a very complex problem at the beginning, or something that you need to spend some time, but in the end it's really easy to build. So, how to attack the trusted BSD? I will not go through all this. Essentially, there's a very important structure, the one, which is a global variable that contains the information about trusted BSD, as the number of policies that execute and all the policies that are loaded in the system. This is the structure for each policy. This is an array that contains all the policies, and this is the policy configuration. For example, we can see the name, full name, and this is what contains the function pointer or the hooks. And this points to another structure, which is a really big structure with all the hooks available in the system. What you do, you register a callback. You say, I want to, for example, to get a hook that every time the access function is executed, I want to get a callback. So you put a function pointer there to your function that will process this. And that's what I told you. No way. Okay, you can go about this. You can see the code. It's very easy. Basically, you do yourself the work. You install these structures, install a new policy, then you set the pointers in that array. There's something to facilitate your work, which is the array is already allocated, so we don't need to allocate memory. They pre-allocate an array with, I think it's 256 or 512 entries. So you just find a slot there, you put there, and that's it. Then to start your model, which is what we are going to use to get code execution, you just increase and say to the system, there's another module, and then the system will go to the list and see, okay, these ones to get the callback, I will send the callback. And that's when we start the rootkit. In our example, I hook this function, the task for PID, because it's very easy, very simple. You just call a PID, a known PID. You can use the PID1, which is launchd, which is the equivalent to init in Linux. So you know that process is always there. You call it, and your rootkit code is executed. You probably want to add some kind of fuse, so your code is not executed. For example, if other code is calling the same function, you get your rootkit executed. So you just need to execute once, you put a fuse there, and that's it. Then you want to clean up all the stuff. You don't want to leave a trace that you abused the trusted B policy. So you decrease the fields, the number of loaded policies. There's no problem in doing this in runtime. And then you remove all the memory that you allocated and all that stuff. You just leave the rootkit in memory. Let me show you the demo. Okay, this is one of the versions. I call them loaders, kernel loaders. This is the version that uses this way of doing. This version also has the Google exploit. I weaponize this one. This version on the VM is still vulnerable to this, so I'm going to execute this kernel extension. Blah blah blah. It's loaded, or hopefully. This is a very program. I can see. This is a kernel extension that I built for anti-debugging. So some processes they have anti-debugging. This will do anti-debugging for that. So I'm going to connect to the kernel extension. Okay, it's connected, and let me show you. Okay, GDB. This is a sample code that has anti-debugging. I'm running, and the debugger is found. So I enable the anti-debugging, run again, no debugger found. So it's running. I loaded code from a normal user using the Google exploits with this loader. And I can show you there's nothing in the sleeves, nothing. Even the kernel wasn't The kernel extension isn't loaded using the system stuff, was loaded directly with this trick. And let me show you the last trick. Because we are loading the buffer, we need the rootkit buffer. We can, for example, load the remote rootkits. Okay. And here it is. This came from my site. This is the reason why it's running on a VM, because I don't know if it could get hacked, and I would be demo and getting hacked myself. So the payload for this, it just does a printf, nothing complicated, came from my website. So, for example, you can have the loader and you can have the payload on a remote website. Then you can clean up, and forensics cannot get probably not much information from the rootkit. So the technique is very powerful because it allows you to do this kind of stuff. Next technique. If you come from Linux, sorry for the reference to Linux. I used to work with Linux a lot. There used to be the KMEM device, which allowed you to access the kernel memory directly. It's something that is closed now. Also, the dev/mem is also closed, or it's protected, because essentially you could access kernel memory directly from that device. This option exists in macOS. It's not activated by default because it's so powerful. You can enable it, for example, for testing and debugging. You just need to go to that configuration or to NVIDIA RAM setting and set keymem equals to 1. Apple introduced it in Mavericks, this kernel extension, Apple HW Access kernel extension. It allows you to read and write access to physical memory. This is the trick, physical memory. So you can read and write up to 64 bits of memory. You don't have a full control, so you have to send requests 64 bits. It takes a while, but it does this. When I saw this, I was like, the fuck? Are you guys doing? Yes, they did this. Once again, I saw this thing implemented in a Hackintosh forum, which is running macOS in normal computer hardware, and at the time it didn't make a click. Okay, yeah, but because the guy was complaining, oh, this can crash the system and blah, 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 and it didn't make a click. So I was developing the first technique, and my brain connected finally the dots. Let's try to use this function to use the same, because I have the core techniques, and maybe I can use this feature to do the same. Let me bypass. This is the reasons why they implemented this framework. There was a debugging framework shut. It was a kernel extension. They converted to a private framework, because these debugging tools need to connect to the kernel. They probably created this kernel extension because it's the only thing I can find in the system that uses this. What we can do with this kernel extension or this feature? We can read and write every single bit available. Almost you will understand why it's there. And we can bypass all the read-only protections that I've shown you, because we are accessing the physical memory. So page tables protection doesn't matter. We cannot allocate memory. We cannot change memory protections, and we cannot once again execute code directly. So there are some restrictions once again, and we need to bypass them. This is how to use the function. Let me bypass it. It's very easy. It's service. You send. There are only two structures involved. A request for in and out. If you want to read, you say, I want to read up to 64 bits, and I want to read from this address. And then you get the contents in the out structure. This passing a 0 is to read. The function is executed, and you get the data, and then you can copy the data if you are reading. To write is more or less the same. You just this is right. Yeah. Essentially, you copy the data that you want to write in the structure, and the out you get it went okay or not. How to exploit this? What we need, again, the same steps. We need to copy the rootkit code. We need to fix the locations. That's the easy part now, and we need to start the rootkits. What are the problems with this feature? We need to find memory, because we cannot allocate memory, as I told you. We can find free space on the system. For For example, the kernel header, usually it's not guaranteed, but there is usually space from the header to the first place where code is. There's usually some alignment space, which is essentially 0, 0, 0, everything 0. That memory is executable. So if you find space there, you can use it for executing stuff. Kernel extensions, they have also alignment space. We can try to put there. You can overwrite kernel functions. For example, what in the morning Shelter was doing. Gets a function that you, for example, NFS stuff. If you are attacking a target that you know they are not using NFS. NFS is default on Mac kernel, so you just write that stuff and that's it. Or you can allocate memory via shellcode. Essentially, you just need a few bytes for the shellcode, allocate memory, and then you do whatever you want. Code execution. It's easier here because since we can bypass all the read protections, we can use the syscall tables. You can go very complex and use the same trusted BSD. You can hook a kernel function because we can write to anywhere. So you can be very creative about that. The same steps, find the kernel is similar. You want to find the amount of available memory because we are going to try to read from the kernel. We need to brute force some stuff, so you don't want to go out of bounds because if you go out of bounds here, it's a kernel panic right away. You need to find where the kernel is in physical memory. You need to compute the rootkit size, allocate kernel memory, writes, and everything else. I decided to attack the syscall table because it's the easiest method. There's no point in complicating. It's very easy to find the table. There are many places that are free. You use one of the free places, you know the syscall number, you call that syscall, and that's it. And then you call that syscall and start the rootkit. This is the same stuff. It's very easy to find the kernel the available system memory. There's a function for that. Anyway, it's possible to read. I told you it's possible to read every bit in VMs. There are two solutions for this. There's the smart solution and there's the brute force solution. The smart solution is exploiting some way of the kernel. When your system starts, there's nothing in memory. So the kernel is put there in memory, and then it's slid somewhere depending on the offset. So what you can do, you can read the address where the kernel is from the disk. That is the original address on the system. Then you already got the slide, so you know where the kernel is in virtual memory. What you can do, you clear the highest 32 bits, because physical memory, you have 32 bits there, and you know where the kernel is. That's it. It's a very easy trick to get the physical location. You can use the brute force solution, which is start from 0, go to the amount of system, and find where the kernel is. This brings a problem. I was very happy with the solution. I didn't remember it at the time. Yeah, this works on a VM. First time I put on a physical machine, bang, kernel panic. What? And there is a reason, of course. You have machine check exceptions, which is you have a lot of stuff, devices and everything that is mapped on physical memory, usually on very low addresses. So if you try to read from that stuff, kernel panic. This is the reason why you cannot do this in physical machines. These are some tricks that I have to bypass, some stuff. This is what I told you, the alignment space between the text, which contains also the headers and the data segments. You can put stuff there. For example, in Mavericks, it's not enough. You cannot put a rootkit there, full rootkits. In Yosemite, at least on that version, the 0.0, there is enough space. You can put a rootkit there. So it depends. Usually, my solution or my best solution is to put a small shell code, allocate memory, and put everything there. Just a warning, the kernel extensions are not wired, as I told you. So if you put there, you'll get page faults. If you want to use a shell code, use this function. Kmem allocate contig, which allocates you contiguous memory. You can use the normal memory allocation functions. The problem with those functions is that it's not guaranteed that the physical memory, it will be contiguous. So you will need to find this piece of memory where each page would be located. This is too much work. there is a function that guarantees you to give you physical memory that is contiguous. So why complicate what can be simple? This is the shell code we can demo and look. But it, I don't have the size. I think it's like 200 bytes or something. The shell code that allocates, protects memory, and gets everything that you need to put the rootkit there. Same thing. Find. Okay. To find the syscall table, there are some signatures. For example, you know where a certain function is because you can read the kernel from the disk. You know, for example, a syscall will be located at this address. You just need to go through all the kernel memory, find where this address is, and you know where the systable is. And this is how we start the rootkit. It's just called the syscall that you hooked, and that's it. I have to bypass it. Just one detail. If you want to execute code in multi-core CPUs, essentially everything new is multi-core. You have a lot of cores. There is this function, MP rendezvous. It was presented by Nemo in an old FRAC article. It guarantees you execution on all cores of the machine. So for example, if you were using the trick to disable the CR0 register, you need to guarantee that the execution happens on all the cores because this register is per core. So for example, you disable this on one core, that core is working, okay, but then another core tries to execute rootkit code, kernel panic because that core has a protection enabled. So this is just a very small trick. Let me put another demo very quickly. So this is a VM running the latest Yosemite that was released this week, 10.10.4. And this is the second version. Okay. Once again, the same rootkit payload. So it's locating. You can see it takes a lot more time because of the 64 bits maximum request. So we need to send a lot of requests. It's chasing the kernel or everything else. And okay, you saw it. It's there. The rootkit was executed with using this trick, so we can do the same rootkit by passing all the protections that there are against this. Conclusions. Hopefully, I will convince you that OSX securities, don't tell anyone, crap. Total crap. There's a funny thing about this. As I told you, I presented this first in Japan, and months ago or something, I got feedback. And the first comment that they sent me was from an attendee. Yes, I know Apple stuff is really broken, but it's not nice to call Apple poop. And I love that quote because I don't know what was the translation to Japanese. It probably wasn't that funny. But because the guy was really, don't call poop to Apple. The Japanese are really nice guys. Conclusions. Hopefully I convince you, or you are convinced that the kernel extension code signing as it is useless because it's running on ring 3. If they don't put on rings or on the kernel ring 0, it's not there's no point in doing it. Don't trust it as a security measure. There are some blogs, people telling, yes, there's kernel extension code signing, it's a security feature. Don't trust it because it's useless. And my question to Apple when I was there, if it's not a security feature, then why it does even exist? Because if you are designing something to protect, at least do it right. Some problems that I told you or that I showed you, there is no official product life policy. For example, Apple releases patches for Yosemite, doesn't release the same patches for Mavericks. So you don't know. I still run, this laptop is running Yosemite, but my main desktop is still Mavericks. I don't know. For example, they release Safari patches for Lion, which is a really old version, but they don't release security patches. So you don't know. At least Windows, Microsoft told you, Windows XP, it's dead. Unless you pay 20 million like the Navy in the US, but it's dead. Or at least there will be no patches for this. Essentially, you either upgrade or you are vulnerable. And even if you upgrade, you are still vulnerable because 10.4 is still vulnerable. Apple knows the bug. Apple saw the presentation, so it's crazy. This is my personal fight. I tell them this a lot. Your strategy is essentially reactive and not proactive. And you know this. Why? Because I released that 0 day on the E5 like 3 or 4 weeks ago. And Apple, this week, very surprisingly to me, they released the patch to the E5 bug. So finally, and they released to all the old machines, for example, 5-year-old machines, they released the patch. And they don't do this. Why they did this? My personal opinion is that they had bad publicity because that stuff went on everywhere. They don't like bad publicity. And so they react to the issues and they are not proactive on that. They try to be proactive. For example, they built rootless, but at least the system like it's designed now, it's a joke because for example, you attach to the KXT process, you patch it. These 2 bugs are still working there, so I don't know what they are doing. If you want to look at the code, it's available on the GitHub. Go there, there's tons of code. It's fun to look. This code is very well commented. People were telling me at CCN, yes, it's amazing on your slides, everything is very commented. When I do rootkits, I don't put comments, I like to do it. Because I never know what I'm doing or what I did the week before. I'm always changing stuff, so it's good to comment. This is my blog, it's very easy to memorize for the podcast people. You have the GitHub. Feel free to email me if you have any doubt or if you have any issue. There's a small community on Freenode, OSX RE. If you have any problem with the Macs or if you are reversing or hacking stuff, come there. You have Mimo there and other known guys from the macOS scene. Feel free to come there and feel free to put your problems. That's it.